Hello students, welcome back. So in this session, we're going to be covering variance and standard deviation of population. So what exactly is variance? Well, the word variance contains the word varies in it. So in essence, it measures like how much your data varies around its mean, like how much is it different from the mean value. So this is the real definition of your variance. It basically measures how much dispersed, okay, or spread or you scattered your data is from its mean value. So the way you measure variance is using this formula right here. So let's say you have these data points, x1, x2, xn. This could be anything. This could be height of somebody. This could be age. This could be temperature. This could be anything. So let's say this data set is given to you and you can calculate its mean. The way you calculate mean of your data is basically to just take all the values and divide by the count. So after you calculate your mean, you can calculate the variance using this formula. And I'll show you in a minute how this is done through an example. Now, one of the problem with variance, it can be difficult to interpret, and that's because you see there's a square term over here, okay, because of this square term. So let's say your data is in centimeter, okay. So now, since you're squaring every single term, your variance will come out to be in centimeter square. And because it is centimeter square, it can be a little bit tricky to interpret. This is where you get standard deviation. This comes to and help you out. So what standard deviation does, it takes the square root of variance. Okay, it's taking a square root, and that's this way it gets rid of the this square terms over there. So now, if your data is in centimeter, okay, and then you calculate variance, and then you calculate your standard deviation, your unit will come back into centimeter. So it is easy to interpret. That's why you need standard deviation. So let's try to understand this variance and standard deviation through an example. Let's say you have a data, and this data could be a income of a population. Okay, this could be monthly income. So some people, so let's say somebody's making this amount of money, somebody's making this, someone's this, and so on and so forth. So here the size of your data is 10, and here my mean value basically would be, in essence, I'll be taking the adding all the values, okay, and I'm dividing by the total count. So that's what I'm doing over here. I'm taking all the values and I'm dividing by 10, and my mean comes out to be 5. Now, just by looking at this data, you can tell, okay, so there is some spread over here. There is some spread around the mean value. My mean value is 5, and you can see some values are 1, 1, 0, 0, 5, 9, 9, 10, 10, 5. So they are spread around 5. So let's calculate the variance, and let's see how it captures the notion of spreadness. So this is the formula I'm using, okay, and this is my formula. Basically, I expanded this formula, and then I'm actually putting my 1 minus 5 square, right? 1 minus 5 square, actually this square right there, plus 1 minus 5 square again, because your 1 is this one right there. The second one is this one. Then your next number is 0. So it's going to become 0 minus 5 square, okay? And then the next one is going to be 0 again. Then 0 minus 5 square and 5 minus 5 square because of this. And basically, I just put all the numbers and I subtract mean from them. And then I square the numbers. Okay, and then I divide by 10 and my variance comes out to be 16.8. So my standard deviation is going to be square root of the variance, which is 4.1. Now the unit of my variance in this case would be, let's say this money is in dollar, okay, or maybe it could be in rupees. Okay, it doesn't matter. But if this is in dollar or rupees, this is going to become dollar square, okay, or is this going to become rupees square? Now, when I take the under root of that, my unit will come back to its original form, dollar or rupees, depending on which unit you're working with. Now, let's try to see how this data looks like, okay? So let's plot this data on a number line. So I have 1, 1, 0, 0, 5, 9, 9. So basically, I plotted these points over here. There's each x over here represents one data point, okay? So you can see two values over here, two values over here, and two values over here, and two values and two values over here. And this is my mean right here, 5. Okay, and you can see that these 10 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, these 10 points are kind of like spread around this number 5, where 5 is my mean value. You can see there is some spreadness over here. Okay, now let's try to look at another example. This data, okay, 4, 3, 5, 6, 7, you can see that it is spread but not as much, and this could be representing, let's say, a package weight in a production line. So when you work in an industry, in a factory, and the weight the packages comes to you, generally they tend to be for the most part consistent. So if you're an operator, or let's say you have a machine and your job is to weigh the packages, and your machine only weighs up to maybe, like, 4 kilogram to maybe 5 or 6 kilogram, then you're going to see your numbers like this: 4, 3, 5, so on and so forth. So here your spread around the mean is less. So in this case, my size is n, okay, my size is 10, and let's calculate my mean. This is my mean right there. Okay, and you can tell that my spread in this case is a little bit low, or very low, or very less compared around my mean value, which is 4.8. So let's calculate my variance. I calculate my variance right here, and my answer comes out to be 1.56. So this is my variance. Okay, take the square root of that, 1.3 kilograms. So my standard deviation is 1.3 kilogram. In this case, my data is less dispersed. Okay, the variance in this case actually went down. So if you go back to the previous slide, you're gonna see my standard deviation was 4.1. Now my standard deviation is 1.3. Let's try to plot these numbers on the number line. So I'm plotting these points right here on the number line. And as I plot, you can see that this is my mean value, okay? And each x over here, they represent my data point right here. So I'm plotting 4, 3, 5. You can see there's a 4 right here, there's a 3, then there is a 5, okay? There's a 5 right there. Then a 6, 7, 3, there's 6 right there, 6, 7, and there's another 3 right there. So basically, I plot all the points, and you can see that all the points, they are spread, they're very closely spread around 5 your 5 basically, or I can say 4.8, where 4.8 is your mean value. On the other hand, the previous data, if you looked over here, they were a little bit more spread out. Okay, all right, now let's take a look at the last example here. This data right here, as you can see, is all 5 5 5 5 5. You can tell there is no spread over here. Basically, all numbers are same. This could represent maybe a time that it takes for each job to go from one station to the next station in an assembly line. Maybe that assembly line requires a high precision, so the time it takes to job to go from one machine to the next machine is 5 seconds. So here my size is again 10, and I calculate my mean. It comes out to be 5. Okay, and then I do my formula right there. Okay, my variance formula. Then I calculate my variance, and as you can see, it comes out to be 0. My variance is 0 because all values are 0. So sorry, all values are 5. So 5 minus 5 is 0 for each one of them. Okay, and the answer comes out to be 0. Standard deviation, take square root, answer is 0. The data is not dispersed at all. 0 variance in the data, and you can see that all my data is 555. It's all spread over here. So if you look at this one, 0 variance, there is no spread of the data. Come back to this over here, some variance, right? There is some spread around of the data around the mean value. Go to the next slide, a previous slide, the first one, and as you can see, there was a large spread in the data. So this is how your variance is actually works. It actually calculates, it computes the variance of the spread in your data. So the conclusion is this, that if all your data points are close to the mean, then your variance is going to be small. Your data is going to be less dispersed or less spread. On the other hand, if your data points are far from the mean, then your variance is going to be large. Your data will be more spread, or it will be having more dispersion. So one last example, I wanted to show you how standard deviation controls dispersion and spread of distribution curve. So this is 100 samples. Okay, this is 100 sample points. All right, and I took it from a data points which had like 1,050 data points over there. Now this one actually had a high standard deviation. So this is my data right here. Okay, this one, and this one actually had the sample. The mean value was 5, and my standard deviation was 4 for this data point. And I plotted this. Okay, so this is where the plot I did. And as you can see, my standard deviation is 4. Okay, so this is my 4 right here. This is my 4 standard deviation. Then I took another 100 sample. Okay, this one had a low standard deviation. Okay, the low standard deviation. And again, my mean was same. So the mean in this case is 5, and the mean in this second one is also 5. But look at my standard deviation is 1. So if my standard deviation went from 4 to 1, look at your curve right here. This is my distribution curve. And as you can see, your distribution curve actually went like this. Your standard deviation is low. So there is almost like a spike over there. So your spread actually has become smaller. So this one has a high spread, and this one right here has a low spread. Now, why do we need to measure variance and standard deviation? What is the point? Well, the short answer is variance is for mathematics and standard deviation is for humans. So variance basically, as I said, it measures the average square distance from the mean. So because you're squaring everything, your answer will come out to be in square. So let's say you measure things in centimeter, your variance will be in square centimeter. Squared units are not very easy to understand, easy to interpret by human beings. So you cannot really say the spread of your height is 100 centimeters square. That doesn't make sense, okay? On the other hand, if I square root this number, Okay, then I can just say that, hey, if your mean height is 170 centimeter, and then I can say that your standard deviation is 10 centimeters. So I can immediately say that, you can interpret that as saying that most of your data is within 10 centimeter above or below your mean value. So I can interpret that. So the variance is 100 centimeter square is not easily interpretable by our brain. Now comes your population variance and sample variance. So what's the difference? If you have a population of size n, and these are the values x1, x2, all the way to xn, then the population variance is given by this formula. Okay. In this case, your xi, each one of the xi is a individual value. Your population mean is given by, basically you take all the values, okay, and divide by the total count. That's your population mean right there. N is the total size of your population. On the other hand, if you have a sample, okay, a sample of size n drawn from a population, okay, it's drawn from a population, then your sample variance is going to be this formula. Note the difference between this and this. Over here, first of all, I'm using sigma squared using to denote this thing. Over here, I'm using s squared. So in literature, you'll find s squared. Generally, they use s squared to denote sample variance. Another thing is that they divide by n minus 1. Okay. Over here, I was dividing by the total. So that's one of the essential difference. And so over here, your sample mean is this. This is my sample mean. So your x bar is the sample mean, not the population mean. Here, your mu was your population mean. This is your sample mean. So these are the essential difference. So for population variance, you divide by n, and for sample variance, you divide by n minus 1. Now, when your n becomes very large, your result is always going to be same. So if, let's say your size of your data set is let's say your n is 1000, okay, 1000. So you divide a number by 1000, or you divide a number by n minus 1, which is almost 999. Your answer would be pretty much similar. It's almost going to be identical, not going to be much different. Now the question becomes, how do you decide which variance to use? Should I use population or should I use sample? Well, if you're analyzing all the data from the group, then use population. On the other hand, if you're analyzing a subset, a small part of the full group, you're not analyzing the whole group, but you're only analyzing part of the group, then you should use a sample. Okay. So let's try to understand this through an example. Situation: you record heights of all 100 students in a school. Let's say you have a school, and in that school there are only 100 people, and you record all the heights. In that case, you're working with population. In that case, you're going to divide by n. You're going to divide by 100. Okay, so your n in this case is going to be 100. On the other hand, if you're working with the same school, and let's say you took a random sample of 10 students, okay, you're not taking the whole population, you just took a random sample of 10 students to estimate the average height in the school. In that case, you're working with sample. All right, so in that case, you're going to divide by n minus 1. In other words, you're going to divide by 10 minus 1, which is 9. Okay. All right. uh, this one right here. Let's say you analyzed every product that is made in a factory in one day. Since you analyze every single product, you're working with population. You're going to divide by n. All right. On the other hand, if in the same factory, if you tested 20 products, okay, tomorrow you only tested 20 random products, in that case, you're working with a sample, so you're going to divide by n minus 1. In this case, n minus 1 would be 19. 20 minus 1, 19.